Hello everyone and welcome to size reduction of powders experiment, calculations and data analysis. Our experiment object to study the efficiency of ball mill and to study the effect of time on particle size and particle size distribution. But our main objective was to estimate the optimal milling time for sucrose size reduction using a ball mill operated at 30 rpm. To estimate optimal milling time, we need to construct optimum milling time curve, which is plotted as median particle size versus milling time, as you can see in the attached figure. Optimal milling time curve either shows a plateau or a slightly decreasing terminal phase. Always add curve tangents to estimate optimal milling time. To estimate median particle size at each sampling time, particle size analysis is required for each sample. How? Via building up our Microsoft Excel tables, we can do so. Here is a table shows the results you gained during the experiment. Now, to do particle size analysis for each sample, we have to build up the following tables. First, you have to calculate the net weight. The net weight, also known as the frequency or retained weight, and is equal to gross weight minus tear weight. Now, build up the following table. Shows the particle size intervals based on sieve spore sizes you used. Determine particle size intervals lower limits. Particle size interval lower limits are the point at which each interval starts, while particle size intervals upper limits are the end of each particle size intervals. Notice here, we assume that the last interval, which is 1.4 to 2 millimeters, have an upper limit of 2 millimeters. Why? Because 2 millimeters pore size guarantee that all particles will pass, even those unmilled sucrose. Now, calculate each particle size interval midpoint, of course in millimeter. Particle size interval midpoint equals to particle size interval lower limit plus particle size interval upper limit divided by 2. Now, as you can see, we arrange net weights to each corresponding interval, particle size interval. Here we will need to calculate percent retained. Percent retained is equal to amount retained or net weight or frequency in grams divided by sample weight. Here our sample weight is 50 grams. Now, calculate cumulative percent over size, which is equal to, by definition, to the percentage of particles that have particle sizes larger than the interval lower limit. Then it is for the first interval equivalent to the amount retained in all particle size intervals, because all particles are larger than this interval lower limit, which is 0. Sum these and divide by the summation of net weights. Notice here we have a cell in which we calculated samples net weights. But for the second interval, it will be equal to the amount retained in this interval plus all larger intervals, which makes sense because only particles that could pass or did pass the sieve, the lower limit of this interval, is smaller than it. And this will be done for all of our particle size intervals. Now, calculate cumulative percent undersize, which is, by definition, the percentage of particles that have particle size smaller than the interval upper limit. Then, for the first interval, it will be equal to the amount of particles retained in this interval divided by the summation of net weights times 100%. But for the second interval, it will be equal to the amount of particles, the net weight in this interval plus the net weight in the previous interval, because only particles that did pass the second interval upper limits are smaller, and those will include the particles in the same interval and the particles in the interval below it. Continue doing so till you find that the cumulative percentage undersize in the final interval is equal to the summation of all particles, since all particles are smaller than its upper limit. Why? Because they did pass its upper limit. Now, plot cumulative percentages oversize versus particle size intervals lower limits. Use scatter charts with markers and smooth lines. Please add the series title, which is cumulative percentages over size, and the second series will be cumulative percent under size. But in this curve, you will plot the interval's upper limits on the x-axis, and you will select for the y-axis the cumulative percentages or under size. The cumulative percentages under size. Add the chart title and the axis titles. For this sample, which was unmilled sucrose, the chart title will be Unmilled Sucrose Particle Size Analysis. And of course, the y-axis is or represent cumulative percent, and the x-axis do represent the pore sizes in millimeter. The two curves should have their intersection point or a cross point at 50% cumulative percent as y-coordinate, and this represents the 50th percentile. 50th percentiles means that 50% of the particles are below the x-coordinate of this point, and 50% of the particles have their sizes larger than x-coordinate number. And 50th percentile is, by definition, the same as median particle size. Then the x-coordinate of the intersection point, which is 50%, and y-coordinate is the median particle size. Here I'm trying to enlarge the chart to make it easier for you to figure out the points I'm talking about. While submitting your report, please use suitable typing volume. What if we only have the values for the cumulative percentage over size? Can we estimate the median particle size? Yes, we can, because simply these two curves we are plotting do represent the same data and will have the same median particle size. Again, if we only have the values of one of the percentages, whether the oversize or the undersize, simply the x-coordinate of 50% cumulative percent will be the median particle size. Now we have to repeat exactly the same calculations to estimate the median particle size for all samples. The shown example again is for unmilled sucrose. Now we are starting the tables for 10-minute milled sample, sucrose sample. Here we have only to change the gross weight, which will be the gross weight for the gross weights generated at 10 minutes. Accordingly, and if we are using the Excel equations correctly, everything will change. Having doing so, now we will have the data, the median particle size at each time. Use scatter chart with smooth lines and intervals to plot median particle size in millimeters versus milling time in minutes. As you can see, we are adding the tangents for the terminal and the initial part of the curve to estimate the optimum milling time. Please watch carefully. Also, we will need to plot frequency distribution curves. These curves are plotted as percent retained versus particle size intervals midpoints. Plot all samples on the same chart. Again, use scatter charts with smooth lines and markers. Please here notice the differences between charts at the 5 sampling points. You can see the frequency distribution curve of unmilled sucrose has the highest x-coordinate, which means particle size of its peak. As milling time is increasing, the curves will have smaller x-coordinate of its peak and higher percentages of particles retained on sieves with smaller pore sizes. Also, you will see that the distances between the curves will get smaller and smaller as we are approaching the optimum milling time. Now, please build your portfolio pages. Use an Word document with the preset layout to submit the results first, the calculations and data analysis. Also, as we said, you can prepare this template and keep it for future. Use it in this experiment and all upcoming experiments. Now, just copy and paste Excel tables and charts. Always start with results tables, then calculations and data analysis. Here are some questions for you to answer. Most of these questions, if not all of them, have been covered during discussions and experimental part. But again, the questions are, upon increasing the milling time, how do frequency distribution curves peaks change and shifted with respect to each axis? Describe changes in the distances between curves and correlate these distances to the optimum milling time. How can milling chamber filling volume affect milling process? Remember, overfilled milling chambers will cause what? Will cause caching effect, and underfilled milling chambers will lead to less encounters of particles with each other and the grinding medium. How can used milling speed affect milling time? As we discussed this in your manual with respect to gravitational effect and centrifugation effect. What may happen if the sieve agitation time was decreased? How would this affect the estimated milling median particle sizes? Simply, if the sieve's agitation time was decreased, there will be not enough time for particles to be classified, and some particles, despite the fact they have small particle size, they will remain in the upper sieves. This may contribute toward the estimated median particle size to be higher than expected, higher or overestimated. What may happen if the sieve agitation force was increased? This will only affect particles or friable particles that are subjected to breakdown upon stronger agitation forces, which will lead to smaller median particle size than expected. There are 4 mechanisms of size reduction: impact, attrition, shearing, and compression. Describe each. This should be done based on your theoretical knowledge. Of these mechanisms, what are the mechanisms of size reduction in ball mill? This was discussed in the practical part. Thank you all for watching.